Okay, so thank you all for joining this webinar. Today we're going to talk about machine learning with Apache Flink, and I'm very happy to have two guests today, but only one has managed to join the Zoom yet, so the other one is still trying, but I would still like to start this event now. So one interviewee that we have in the session today is Dong, and the other one is Zhipeng. They are both committers of Apache Flink, and they're working on the Flink ML project and related ecosystem projects of Flink. My name is Robert Metzger. I'm also a committer and PMC member in Apache Flink, and I work at Decodable as a software engineer, working mostly on the Flink integration, Flink service at Decodable. Dong, do you want to quickly introduce yourself to our audience?
Yes, sure. And first of all, thank you, Robert, for the introduction and for organizing this session. It's a very good chance to share my experience with Flink ML and also discuss any opportunities with Flink ML. And personally, I am currently a staff engineer at Alibaba, and I focus mostly on developing Flink and the ecosystem around Flink. And prior to joining Alibaba, I was staff engineer at LinkedIn and also engineer at Google, developing Kafka and TensorFlow respectively. So my expertise mostly revolve around big data and some machine learning things. Yes.
Great. That sounds super exciting. So you seem to have the right background for working on machine learning with Apache Flink. So maybe to get started, what kind of machine learning tasks are suitable for Flink from a high-level point of view? Because in my mind, Flink is mostly used for streaming, and what I learned in school about machine learning is that it requires a lot of batch processing for iterating over models and so on. So what are, from a conceptual point of view, features of Flink that make it well suited for machine learning?
I think in terms of functionality, we know that Flink can do both streaming and batching. And specifically, Flink is mostly advantageous in doing streaming things, and which makes it pretty suited for doing real-time machine learning. As we know, I think machine learning is moving to be more real-time, and people want to get inference results and even the training more and more real-time. So in that area, I think Flink streaming capability can help a lot. And from our practical experience, we have seen that many companies and users in China are using Flink to generate, for example, the features, real-time features for machine learning things, such as the number of counts of user clicks per user, per item in a given time window. And Flink is doing pretty well than alternative solutions in this area. This is one thing that we have seen where Flink is doing well. And the other part where we expect Flink can do well is due to real-time machine learning inference. For example, that is similar to, for example, the bucketizer and strings indexer and other feature engineering operators, things like that. Whenever you want to do real-time inference, I think Flink does well. Yes.
And what kind of models can you infer in real time?
For example, I think if you first, I think feature engineering is a general thing that can be that is part of machine learning, and its output can be used for both deep learning and the traditional models. Flink can also be used to do machine learning for traditional models such as k-means, naive Bayes, and so on. On the other hand, I think however Flink can do similarly to the alternative solutions, this is currently not an area that Flink is particularly more advantageous than alternative solutions. So overall, I think the big picture is Flink can excel than alternative solution in doing feature engineering and so on, and then Flink can do similarly in the long term than compared to alternative solutions in terms of doing training and the iterative batch training. So the overall, when combining everything into one solution, Flink can be advantageous in the overall. Yes, when you combine everything, do you use one framework to do everything?
I understand. Okay, and what are common? So you mentioned alternative solutions. So what are the main competitors to Flink as an overall solution that you see in China or in general?
Yes, I think we have seen Flink and Spark compete with each other in many areas. As we know, Spark is used much more than Flink in the batching computation scenario. Flink and is used relatively more in terms of streaming scenario. I think both solutions are trying to catch up with the other one in the other area. For example, I think Spark recently launched Databricks recently launched a project called Lightspeed, where they are trying to say they will catch up in terms of streaming capability. And Flink, at least in Alibaba side, we are spending a lot of effort trying to catch up in terms of the batching capability. The Flink 1.16 release are trying to hopefully reach 80% throughput as Spark in the common for the common batching jobs that users will see. Oh, well, what's the original question? I lost.
So what are the competitors of Flink in the machine learning space?
Okay, yes. So I think the competitor, the most well-known competitor will be the Spark ML. As we know, Spark has a pretty well-developed machine learning library with much more algorithms coverage than Flink. These libraries are well tested and used in companies like Uber. So this is an example that Flink is trying to catch up and learn from. I think, at least for now, Spark ML is the obviously more a more mature solution than Flink ML. But in long term, I'm hoping that Flink can take advantage of its streaming capability to earn some users, and then catch up with Spark in terms of this batching computation capability to do the batch training and so on. So that's the situation.
Okay, and so you mentioned that Flink is very popular and faster in feature engineering in general. So what APIs are people using for that, and how are they doing it?
Flink machine learning library currently use both the data stream and the table API in both Java and Python for users to use machine learning library and develop machine learning library operators. And these APIs are batch and stream unified. So people can just use the same set of code for both streaming and batching computation online, nearline, and offline. So that's a very nice feature. And does that answer the question? The API part?
So maybe we should also take one step back, and maybe can you define for me what is feature engineering? Like, what are the common tasks that you have to do when doing feature engineering?
Sure. That's a nice question. The feature engineering, generally speaking, it tries to compute features that is needed for doing the machine learning training and machine learning inference. Common features can be either the count or aggregation of some value in a given time window. For example, the number of users. For example, we can have a stream that basically shows the user click stream, and we want to see the number of user clicks for every user in the last 1 hour. So this is one feature that Flink can calculate by just using a time window and using some sliding window to calculate that count. This is an example. And some other feature engineering things include the string indexer. For example, the item name. Usually, the original value of the item name can be a string. And we might want to encode these string values into some integers or one-hot encoding so that the numerical things are easier and more friendly to be used for training later. And we might also want to do some, for example, do some uniform, change the input numerical values into some uniform distribution so that the later training can be more accurate, things like that. So these are the common feature engineering operators we today see in the Flink and in Spark machine learning library. And since there are some other feature generated things, for example, Flink can also be used to join features from multiple tables into some big table so that that data can be used for training and for inference.
And what's the, let's say, flow of data? So you have a bunch of data sources and you're using, let's say, Flink SQL to aggregate and join. And then where are you writing these features to? Like, how are you persisting them?
Oh, sure. In general, we can categorize the destination of those features into online and offline. Typical online feature stores include, like, for example, Decodable and Redis. These are typically key value stores so that when you are doing the online inference, you can quickly fetch the feature for a given value or for a given key, for example, user ID to do inference. And the common offline feature store includes you can use OSS, object store, and also the HDFS and so on. So these features pretty much rest there, and you can do batch processing to derive more features from these features. And we have also seen people use Kafka to store and transmit online features. For example, so people can, for example, let's say user clicks, right? So user click an advertisement, and we will provide features, and we will also record the historical features that are used to respond to that user click. And then later, if user does buy something, that will be a positive sample, and we want to see what features are used to generate advertisement which leads to this positive click. So that's an example where we will, for example, use Kafka. We will join two streams. One stream is coming from Kafka. That is, okay, there's a positive sample. And join that stream with the data in the Redis key value store, which stores the historical features. Then that forms a real-time training sample data. And we can then feed that sample data into Kafka and have the training job ingest the data from the Kafka to do periodic real-time training. Yes.
Okay, so the architecture of like a Flink-based machine learning setup is basically that you have your data sources, then you have a Flink streaming job or multiple Flink streaming jobs for the feature engineering. Then you're persisting the features into either an online or offline feature store. And then you're using a machine learning system, either Flink streaming again for online training, or Flink batch for offline training, or Spark machine learning, or any other system, TensorFlow, PyTorch, to train your models.
Yes.
Okay.
So you have a lot of choice for training, and the Flink can be used to do feature engineering before the training stage.
Yeah. And so can you do this entire architecture that I just described? Can you do this entirely in Flink?
Yes, technically speaking, you can. But in reality, you usually use the component that provides the best performance and best ecosystem in that area. For example, I would say, practically speaking, if you want to do a batch-based training using the traditional algorithm such as naive Bayes, Spark ML is probably a better choice than Flink ML. And there are many cases you want to use deep learning instead of traditional learning, then TensorFlow or PyTorch is definitely the choice. Flink does not provide deep learning capability and so on. So the best choice depends on the case by case, the actual problem you are trying to solve.
Yeah. So I forgot to mention in the beginning of this webinar that people in the audience are welcome to ask questions. And you can just ask questions and I will try to incorporate them into my own questions, or I will read them. And there's one question now. I will just read it. Flink is an awesome tool, but I see JVM as a limitation for performance. Any thoughts on if core parts of Flink being ported to C++? So I can also answer part of that question. So I don't think that there's any plans for like core Flink, like the runtime, the task scheduler, and the common services in Flink to be ported to C++. But are there any parts of Flink ML, or are there any plans for Flink ML to use other language ecosystems?
Yes, that's a great question. And the short answer is yes. And if you open the, I think we opened the GitHub organization that is called Flink Extended, Flink-Extended, which hosts the Flink ecosystem projects for people to browse and use and contribute. We contribute a project called C-Link, which exactly tackles this problem. The idea of C-Link is to provide the infrastructure and API for people to develop C++ operators using some very efficient library, for example, TensorFlow runtime, to parallelize those operators. And those operators can then be wrapped into the Java operators using the Flink ML API, so that people can just according Flink, use the Flink to parallelize the operators execution across the task managers. And the advantage of using C-Link is that not only can you call this operator for streaming in both the nearline and offline scenarios, you can also reuse the same code operator for the online scenario where you want to respond to user requests in super low latency. And this is where we don't want to deal with the JVM latencies. We want to have very stable and very low latency, which is provided with C++ runtime. Yes.
Okay, so so C-Link, I don't know how to pronounce it. So is this using JNI, or is this using another mechanism for supporting any language?
It is using JNA, which is basically JNI. So we use the JNA API to do that.
Okay. And are there any examples for integration with TensorFlow or anything like common popular frameworks?
Yes, we have. First, we have seen many cases where user use Flink together with TensorFlow to do end-to-end machine learning. The common scenario we see is Flink, the output from Flink will first be synced to a feature store, either online or offline, like Kafka. And then TensorFlow will just read data from the feature store to do training. So in most cases, TensorFlow does not interact with Flink directly. They interact via feature store. On the other hand, we have also seen technically there can be cases where we want to do an online training without having a feature store sitting in between. This is, and we have contributed a project also currently open source in the Flink Extended organization that people can see. The project name is called Deep Learning on Flink. Basically, the idea is that we will start a Flink job. And in one of the Flink job, there's a UDF. The UDF will internally start a TensorFlow process, which will ingest data from Flink and do training. This is useful for online scenario where you don't want to have a Kafka, you don't want to manage Kafka because we know that Kafka might incur additional storage costs. And also it can introduce other benefits such as the coordinated checkpoints between TensorFlow and the Flink job so that you can achieve exactly once end-to-end, things like that. This is the project currently in an early stage. I think it is ready for testing and for you to try it out. And we welcome any feedback. Yes.
Cool. That's very interesting. There's quite a large ecosystem already available that is not in the main repository of Flink, but in the Flink Extended organization. Okay, so I understand that deep learning on Flink is not used in production anywhere. And there's a third project in Flink Extended. It's called AI Flow. Can you also briefly describe what this project is doing?
Sure. So basically, AI Flow is a workflow orchestration platform. It is very similar to Airflow. As we know, Airflow is an Apache project, which allows you to just orchestrate and schedule the execution of many tasks. It's a task graph. The main difference and also the innovation of Airflow is that it introduced the event-based workflow orchestration, which is particularly useful and necessary for streaming scenarios. Let us think about what Airflow with the traditional workflow orchestration tools such as the Airflow and the Kubeflow. Basically, a task can be started or restarted based on the status change of another task in the stream graph. For example, the previous task has ended, then you can start the next task. However, the unique feature of the streaming job is that the job might never end. So its status might never end. What changes is its internal state. And it is not easy to capture or express the change in its internal state in Kubeflow or Airflow. And this can make it challenging to support some example scenarios. For example, let's imagine that in an online machine learning scenario, you might want to periodically start a TensorFlow job every hour to do some training, to do some incremental training based on the data you have received in the last 1 hour. And you want to use the Flink to do feature engineering and generate features needed by the TensorFlow job. And in order to do that, the best way is probably to use the Flink, continuously run this Flink and restart TensorFlow job every 1 hour. But with Airflow, you have some challenging things. That is, when you start a TensorFlow job, you might need to use a timer to start a TensorFlow job, for example, at the exact 1 hour, same minute every hour. But then you might need to, sometimes you might see the data from the Flink job has delayed, maybe due to some traffic spike. And the downstream TensorFlow job either needs to stop or it needs to spin waiting for the data to be ready. It is not just not nice. The best way is for the Flink job to inform the workflow orchestration system when its watermark has reached the hour boundary. Then you can start the next TensorFlow job and so on, right? That's the nicest thing to do. So with the AI flow, basically it provides the API for you to express such logic in an event-based way. You can write a UDF in the Flink job to say when the watermark has reached the expected interval, then it can send an event to Airflow. Airflow then starts the next job according to what the user has specified, and so on. So it completes this scenario nicely. That's basically the motivation of Airflow.
Very interesting. And which runtimes does AI Flow support? Is it just Flink, or does it also support other runtimes? And on which deployment systems does it support Flink?
Basically, the system and the runtime supported by AI Flow is exactly the same as the Airflow. Basically, by design, it is supposed to support K-bias, and also in future we can support Yarn if it is needed. And basically, you can write UDF with the Bash script, the Python script, or it can be a Flink job or a Spark job, and so on. So by design, all these can be supported. Of course, currently our focus is in short term we will focus on K-bias. I think it is the trend as of now, and we will definitely support Flink as the first class citizen, and then we will support Bash and Python. Yes.
Okay, so then there's another question from the audience. What are your thoughts on deploying machine learning into Flink for real-time classification or similar cases?
Can you repeat the question again? Sorry.
What are your thoughts on deploying machine learning into Flink for real-time classification?
real-time classification. Okay, my thoughts is that first, I think there are some traditional algorithm that does classification. I think, for example, logistic regression or something like that. And we have developed Flink ML library to tackle this problem, exact problem. And I believe Flink can achieve the best performance when it's when the low latency is important. And so that's a long-term expectation. As of now, I think we have already, for example, in the most recent Flink ML release, we have done benchmark and compare Flink ML with Spark ML, and on selected algorithms, we found that Flink throughput meet or exceed the Spark ML. On some other algorithms, Flink is falls behind Spark ML, and we have found that we have identified reason. For example, so for some small operator, Flink's operator overhead seems to be higher than Spark operator. So we are working on that. So the short answer is, in the long term, I believe Flink ML can be the best solutions in this area.
Yeah. Are these benchmarks published somewhere?
The benchmarks. Okay.
Yeah.
We have to avoid any or the controversial issue. We haven't published or exactly specified this in the release announcement, but we do provide the benchmark framework and also the script we have used. I mean, the configuration we have used to reproduce benchmark for both Flink ML and Spark ML. Okay, it is not published, but if you request it, we can publish this.
Okay.
We didn't publish just to avoid any controversial issue. Yes.
Yeah. Okay, so now maybe let's talk about the Flink ML project. So now we've talked a bit about machine learning in general, about architecture, about ecosystem projects, but I would also like to talk a bit about Flink ML itself. So where in the machine learning space does Flink ML fit?
I think Flink can do both training, inference, and feature engineering, but it's best at feature engineering as of now. Yes.
And okay. And what are you providing for? So when you described feature engineering earlier, you basically said it's like joining and aggregations. But what is Flink ML providing on top of that? On top of, because Flink itself can do joining and aggregations quite well with various APIs, but what is Flink ML providing on top of that?
Sure. Flink ML can additionally be useful to do feature engineering, where you first need to generate model data. For example, embedding, right? You don't typically, for large models, when you have a lot of inputs and items, you don't manually write the mapping from the user input to the destination value. You train it by using the sample data. For example, how the strings map to one-hot encoding and so on. Whenever you need to generate the model data for such mapping, Flink ML can be useful. This is one scenario. Yes, pretty much everything that Flink ML is useful in feature engineering can be described by this description. Yes.
Is it available for Flink SQL as well, or only for Java, Python?
Oh, currently it is only for Java, Python.
Okay.
I think in the future we will look into how to support this using Flink SQL, but it is not on our roadmap yet.
Okay. Maybe it's also a crazy idea from me. Maybe it doesn't make sense. And so you said, okay, and what about training? So what models can you train, or what kind of training can you do with Flink ML?
Okay. Currently, our target is to meet whatever Spark ML can do. And we have already had, I think, a couple, 5 to 10 training operators in the Flink ML library. It supports traditional algorithms such as the naive-Bayes, logistic regression, k-means, and so on. And we also added 2 online learning algorithms to verify and demonstrate Flink's online learning capability and also to build up its infrastructure. For example, we provide online logistic regression and online k-means. Basically, it keeps ingesting an infinite stream of training data, and you can specify the number of values that will be trained before a new version of model data is generated. And then we have another operator that basically ingests this unbounded stream of model data and then use the model data to do inference, right? Every time a new version is generated, you can use the latest model data to do inference, and model data can be transmitted via Kafka. Yes.
So I'm not a machine learning expert, and so you mentioned now a list of algorithms, but what use cases can you actually implement using these algorithms?
Sure. The use cases, I think, common use cases might include, for example, anomaly detection. Generally, traditional machine learning can be useful for anomaly detection, classification, for example, classify whether an email is spam or not. I did some project like this during my graduate study. And also, the naive can be used for spam filter detection, for example. And what else? I need to check the library name. Basically, okay. That's the closest things I can find in my mind. But I'm sure if we search on Google, there can be much more than what I described now. Yes.
Yeah. And inferencing. So what kind of models can you inference with Flink?
What kind of model I can do inference with Flink? Is that the question? So every training algorithm has an accompanied transformer, which basically does inference for that algorithm. For example, when we say k-means, basically we have an estimator for k-means, which takes the input data and general model data, and we have another k-means model, which is basically a transformer that ingests the model data and use model data to do inference on the input data. So basically, you have an input stream as an additional column on the input stream that basically express the expected inference result for every record, things like that. Yes. So the short answer to that question is we have, for example, logistic regression, k-means, naive Bayes, and so on. All these algorithms have the corresponding inference operator in the Flink ML library.
And there seem to be models available online, like pre-trained models. Does Flink ML support their common standard, like common file formats for these models?
I'm not sure. Maybe I missed that thing. I'm not aware of any open standard that those common machine learning libraries just conform to when expressing their model data. But if there is, I think we will update Flink ML to support that. So I believe it's. Do you have a reference for that open standard?
So there's, for example, this onnx.ai website, the Open Neural Network Exchange. I mean, okay, it's for neural networks.
Yeah, that's right.
So you have to use TensorFlow, I guess, or PyTorch or so to read the models there to use them.
Yes. So I know that one. Yes, for deep neural network, there's such open standards. I think Flink will not directly do the deep learning. It will just use the existing framework for deep learning. So in the traditional model era, probably there's no open standard yet. Yes.
Yeah. Okay. So very recently, Flink ML 2.1 was released. What are the new features of Flink ML 2.1?
Sure. I think the main focus of this release is on maturing the infrastructure in the Flink ML library that are needed to develop machine learning algorithms. To that end, we have hardening and expanding infrastructure with performance optimization tools. For example, we optimize the memory management framework, which allows you to use as much memory, which allows users to specify, for example, the maximum memory that can be used for an operator, and the operator can then automatically fall back to use the desk to spill the data over to desk when the memory has been, when the amount of model data exceeded that threshold to achieve the best performance in all scenarios. And also we added a benchmark framework, which makes it very easy for users to reproduce and test operators' performance, which is not only useful when you develop a new operator, but also very important for developers to make sure that as we evolve the library, the operator's performance can be tracked and make sure we detect any performance problems early on to fix it. So very useful for long term. We also, for the first time, developed the Python SDK so that it is easy for developers to wrap the Java operator into the corresponding Python operator so that the same operators can be useful for both the Java and Python users. And we also, for every algorithms that we have added in the Flink ML library, we have both Java and Python operators, so user can use that off the shelf. Other features include, for example, the full examples for every algorithm, and we have both the Python and Java code as an example, and we extended the Flink ML website to include all those examples to make it very friendly for users to learn how to use Flink ML, things like that. So in addition to that, we basically developed example algorithms, including the online algorithm we just described, to validate the infrastructure, and we validated at least for more than half the operators, Flink ML can meet or exceed the performance of the Spark ML. Yes.
Cool. That's a pretty big release. Very interesting. What are your plans for the next release, for the next version?
That's a very nice question. For the next release, I think the focus will be to develop the off-the-shelf library for the feature engineering use cases, because we believe if the Flink ML wants to attract users and land actual use case, feature engineering will be the most advantageous areas for Flink. And basically, we identified that there are probably around 29 machine feature engineering operators in Spark ML. We will try to first catch up in terms of the operator coverage and implement all those 29 operators in the next 4 to 5 months. And we will also make sure that the performance of these operators, at least more than half of those, needs to meet or exceed the Spark ML. That's our goal. Hopefully we can achieve that. And we will internally also trying to find the use case or the users for those operators so that to actually validate Flink ML's functionality in addressing the real world use cases. And that will be also very useful for Flink ML to attract more and more users to use, validate, and contribute to Flink ML. Yes.
Cool. And what are the what's the long-term vision for Flink ML? So basically, as I understand, we're basically catching up with Spark ML right now. But what's the plan once we've caught up with Spark ML?
I think Flink ML is just one of the many ecosystem projects around Flink. The main goal is to expand Flink's capability to address real-world use case. So for Flink ML, once we first we want to tackle the feature engineering scenarios. After that, I think I probably want to focus more on other ecosystem projects. And for example, let's say a feature store based on Flink, and also AI Flow and so on, and maybe also devote time to make sure that Flink's batch computation capability can meet or exceed that of Spark. I think that is more important than developing the traditional machine learning algorithms in Flink ML. We will see. So that's all these options are on the table. We will see what is more important to the Flink as a whole, instead of just looking at Flink ML.
Yeah. And is Flink ML used in production? Like, are you aware of any production users?
No. Our focus in the next 3 to 5 months is to find production users for use cases for Flink ML. Yes.
So you mentioned a feature store based on Flink. Can you describe what the goal there is? Like what properties would it have? And because Flink is traditionally a processing system, not a storage system. So how do you imagine that?
Sure. First, I think there are 2 example open source projects, open source feature store projects. One is the FEAST, F-E-A-S-T, which was developed more than 5 years ago. And it is one of the most popular open source solutions now. And the other one is the LinkedIn's Feather, which was open source by LinkedIn, I think 2 to 3 months ago. And conceptually, feature store allows you to define, register, and generate features. It allows you to express the feature definition, and then we can start a job, either Flink or Spark or some other engine to actually compute these features, basically feature ETL, right? And the main motivation of using Flink to build the feature store is to take advantage of Flink's streaming and batch unified computation capabilities to generate features. For example, I think LinkedIn Feather are deeply integrated with Spark to generate features. It makes sense when you want the batch features, right, offline features. But when it comes to the streaming features, for example, the number of user clicks in some time window, and Flink is, at least now, can provide better performance than Spark, as we see many users. And so I think if we can provide an alternative solution which uses Flink as the underlying engine to build features, that will not only benefit user, but also benefit Flink's ecosystem. So it benefits both sides, and will help Flink reach more users. That's the purpose. And that's also the edge we are trying to rely on to gain users for this project.
But why aren't we just adding support to LinkedIn Feather or something to also use Flink to generate the features? Like, wouldn't it be easier to use an existing feature store and make it so that it can use Flink?
The amount of work to support a new engine is the amount of work to support Flink in Feather is pretty much the same or even harder than starting a new project. Let me explain it first. I think conceptually, in order to support a new transformation engine, so first, the feature store itself does not provide storage. It uses existing storage, for example, BigQuery, Redis, and so on. The main work of that feature store is to define an SDK for users to express the feature definition, and then compile that definition into the corresponding job, so that that job will be responsible for carry out this computation, read features from one store, and sync the generate feature to another store. That's all what that job does, and what that project does. So basically, I think LinkedIn does that compilation. Compile the SDK's definition into Spark job. And in order to support Flink, it needs to do the same thing, right? Again, totally new code. And basically, that's most of the work that we are needed. I mean, if we write a new project to do that, the amount of work are pretty much similar. And I think whether or not LinkedIn plans to do that depends on their internal needs. I think they are using the Spark because internally it suffices for their use case. But our starting point and motivation are different. We, at least at ID Cloud, we take a lot of ownership in developing Flink. We want Flink to grow well, and we believe Flink can do better than Spark in a lot of cases we care about. So we have more motivations to use Flink to develop new feature store projects than LinkedIn.
Yeah. Okay. So my final question before we look at the questions from the audience is, if somebody's interested in contributing to Flink ML, where can they start?
I think typically for most open source projects, first read our website to learn how to use the existing algorithms, hopefully that users can test out the Flink ML library and provide feedback, comments, or open Jira tickets and so on. That's all kind of contributions we're welcome. And if he has even more time and expertise, we hope users can open PR to contribute algorithms. For example, add a new algorithm that he finds very interesting in Spark ML, and maybe he wants to see if Flink can does better when it comes to the streaming inference, then try to implement it using API and infrastructure and see if it works out. And as long as it conforms to our code standards, we will spend time to review and merge that PR. Yes.
Okay, perfect. So I hope that some people show up after this interview to contribute to Flink ML. Okay, so now I'm happy to forward any questions from the audience to Dong, and then we can discuss them. There's currently only one question that I will read. Could you share any recommendations around checkpoint and save point configuration best practices? So I think this question is unrelated to Flink machine learning. It's a general question regarding Flink. And it's difficult to answer this question just like that, because it really depends on what you want to do with Flink, like whether you want to optimize for fast recovery, then you want to do fast checkpoints, or maybe you cannot do fast checkpoints because you have large state. So creating a checkpoint takes a lot of time. Then I would rather look into things like incremental checkpoints. Yeah, so the answer is it really depends. And my recommendation is to benchmark or test this given your infrastructure and your data. Yeah, so then there's 3 more questions. Do you see Flink ML's future in online machine learning training? I think that's something we actually discussed already. Or maybe do you want to comment on that?
Sure. First, I think online learning is relatively new, and its applications in real world is much less than the alternative things, that means batch training or incremental training. So I think one of the goals, at least for me, is to provide the infra in Flink ML to develop online learning, so that hopefully more people can have interest or may find it easier to develop online learning algorithm based on a library, and hopefully they can first help people find the application of online learning. So I think the application of online learning and the infra and library for developing online learning algorithms, they help each other. So I want to start one point, and hopefully the other point can catch up.
Mm-hmm. Yeah. Do you know if there's any, because like, is there any research papers with interesting online algorithms that are just not implemented yet? Because in my perception, often machine learning has a lot of research and experimental algorithms, and only few of them are actually used in like real world production scenarios.
Right. Indeed, there are very few such applications, but there are indeed some papers that exist. For example, in this release, we added an online logistic regression algorithm that is based on a Google paper. I forgot the name of that paper, but that is the link for that paper is encoded in the code. So I can take it out. Anyone can take it out. So this is one example where we implemented the paper, the algorithm paper into the Flink ML library. But honestly speaking, we haven't actually validated its accuracy using the real-world training data. That's something we plan to do later. But for now, the focus of the current release is on the infra. Yes. So back to the original problems. I hope in the long term, my vision is that in the long term, more and more people can develop online learning algorithms and use that online learning algorithms to tackle real-world problems.
Okay. The next question is, what other machine learning algorithms are on the roadmap?
Currently, or on roadmap, at least in the next 4 to 5 months, we plan to add 29 more feature engineering operators that we found in Spark ML into Flink ML. We don't have any short-term plan to implement more training algorithms. Whether we will add more, if we add more training algorithms in the first stage, we are trying to catch up and add whatever is in the Spark ML into the Flink ML. So the priority depends on what we see later in after 5 months. Yes.
Okay. Then there's a question going back to the feature store. How would that work? Would it be an external data store? Is it embedded within Flink? Would it manifest itself as something similar to Flink state?
Sure, no, it will not be embedded into Flink. The basic idea is, by the way, we plan to open source it in the next 2 to 3 months. The idea is pretty similar to LinkedIn's Feather. Basically, it runs SDK, including DSL language for you to express the feature definition. And then it will allow you, actually relies on you to reuse the existing offline and online feature stores such as HDFS, OSS, Kafka, BigQuery, and so on. It starts a Flink job, which runs and executes your feature definitions, ingests the data from one feature store and syncs the data to another feature store, and so on. So everything happens within the Flink UDF, and the UDF is defined by us outside Flink. Yes.
And the final question is, what are your thoughts on deploying machine learning into a Flink job for real-time classification? I think we answered this question already earlier, right? Yeah, we spoke about real-time classification already. So I think we answered this question earlier in the session. So if you didn't catch the answer, then I would recommend you to check the recording. Okay, there are no further questions. So unless a question shows up now, we are done with this interview. It was really, really interesting to learn more about machine learning with Apache Flink. And maybe we can just do another session in a year or so and see how things have developed, like where are we standing with respect to performance, with respect to catching up to Flink ML, production users, contributions. It sounds like this is a pretty interesting project with a bright future. So do you have any final words? Okay, then
No.
okay, perfect. Yeah, thank you very much for being part of this interview. It was really fun. I learned a lot. And thank you for staying up late. I know it's very late in Shanghai. So thank you very much.
Yeah, my pleasure. Thank you everyone for attending this talk. And thank you, Rob and John, for organizing this event. Thanks a lot.
All right, thank you.
Okay.
Bye-bye.
Thank you. Bye-bye.